Assalamualaikum and good day everyone. Today I would like to present my final project entitled Synthesis of Zinc Sulfide and Silver Phosphate based photocatalyst using impregnation method for photodegradation of rhodamine B. My name is Muhammad Ibrahim bin Ismail and I'm under supervision of Dr. Muhammad Saifuddin bin Muhammad Azam. So here are the overview of my presentation. Firstly, let me start the presentation with the introduction. Direct contamination, particularly in wastewater from sectors such as textile and food processing, is a significant environmental issue. One of the most widely used dye for printing, making textile, and as coloring agent is rhodamine B. Nowadays, there is a lot of worry about its harmful risks on human health and aquatic life. Next is the problem statement. RHB is a component of xenobiotic substance, leading to a lot of worry about its harmful effect on aquatic life and human health, such as skin and eye irritation. Many methods have been used to treat RHB dye, but most of it have its own drawback, including producing sludge, time-consuming and costly. Currently, photocatalysis employed by AOPs have given much attention to mineralize the pollutant. Among of the photocatalysts, silver phosphate stands out. Despite the benefit, the limitations of silver phosphate could not be ruled out. In order to address the limitations of silver phosphate, zinc sulfide is loaded to silver phosphate due to its RHODAMINE, strong redox potential, low toxicity and inexpensive. Above all, the reason I choose zinc sulfide to load it with silver phosphate is because I want to create a novelty between the pairing of two semiconductors, because there is still no other past research using the same two semiconductors. Next, I move on to the objective of my research. The first is to prepare zinc sulfide silver phosphate composite photocatalyst using the impregnation method. Second is to investigate the zinc sulfide silver phosphate composite photocatalyst chemical and physical characteristics. Third is to examine the effectiveness of zinc sulfide and silver phosphate composite photocatalyst on the degradation of RHB. And lastly, to identify the proposed mechanism of the photocatalytic activity RHB using prepared composite. Now we move on to the methodology of my study. The first is synthesis of catalysts. Both catalysts were synthesized using the same method, which is the precipitation method. Next is the synthesis of composite photocatalyst. Impregnation method was utilized to combine silver phosphate with the zinc sulfide, and photodegradation of rhodamine B. 0.025 gram of the photocatalyst was suspended in 20 ml of 10 mg RHB solution, and then it is exposed to visible light for the degradation. Next, we move on to characterization of synthesis catalyst with using instruments such as FTIR, PSEN, and UVs. And photocatalytic performance was studied with the effect of concentration, catalyst, dosage, pH, and scavenger. And lastly, we propose the mechanism for the photocatalyst. Now we move on to the result and discussion. The first is the FTIR characterization. As we can see here, all the dominant peaks for both of the catalysts is present on each catalyst. For the composite catalyst, the tank Z shows the most intense peak. This is due to this is because when there is a shift to higher wavelength, it shows that it has a strong interaction between the two catalysts. Now is the PSEN scanning. We can see that PHOZN has a spherical or cuboidal morphology with a tiny white dots in the center of the structure. Pure silver sulfate shows a typical irregular structure and the distribution of particles of silver and zinc is well dispersed on silver phosphate on picture C. Next is the UV visible result, which is you can see that the 10Z shows the lowest bandgap with 1.82 electron volt. Now for the photocatalytic activity, the 10Z shows the highest. The 10Z shows the highest percent photodegradation. The 5 and 15 Z ratio. This indicates that 10Z is the most optimal ratio. This can be proved by the characterization that shows that 10Z has the lowest bandgap. It has a well dispersed element. It has a strong interaction between both catalysts. Next is the effect of initial concentration for the parameter study. The first is the initial concentration. The best performance of degradation is at 10 ppm. This is because when the RHB concentration is increased, the light absorption in the solution decreases. As the concentration of dye molecules increase, they absorb less light, reducing the amount of light available for photocatalysts. The second effect is the catalyst dosage. The 0.025 gram per liter dosage shows the best performance of photodegradation activity of RGB with 94% photodegradation. The decreasing performance of photodegradation in RHB catalyst dosage means that the solution becomes heavy and hence causes the shielding of light and hinders the light radiation. While when the dosage is increased, it is decreased, it shows that it has reduced active site to initiate the photodegradation. And next is the effect of pH. It was found that when increasing and decreasing the pH will affect the degradation rate of RHB dye. When RHB exposed to acidic and alkaline medium, RHB color instantly degrades to colorless. And now is the effect of scavenger. It is determined that the potassium chlorate. It is determined that the isopropanol hydroxy radical in bulk species plays an important role for Z10Z photocatalyst. And lastly, the proposed mechanism. Potential Z mechanism was determined to be the mechanism of ZAP photocatalyst. Why is it a scheme mechanism? In this case, it occurs because the silver phosphate does not reach the level to produce the superoxide radical anion, while the zinc sulfide does not reach the level to produce the hydroxyl radical. So the combination between the two photocatalysts allows them to generate the radical needed to negate the pollutant. The reaction starts when the photocatalyst is exposed to light, and then the electron on the valence bands of both photocatalysts will excite and move towards the conduction band. The hole generated at the valence band of silver phosphate will react with the water to produce the hydroxyl liquid, while the electron excites at zinc sulfide conduction band will react with the oxygen to produce the superoxide radical anion to degrade the pollutant. The electron here will combine to make the Z scheme mechanism, which focus on the strong redox potential, which is the oxidation at valence band silver phosphate and reduction as production blend of zinc sulfide. Next is the conclusion. Overall, the zinc sulfide loaded on silver phosphate was successfully contributed to enhancing the photodegradation of rhodamine B under visible light. The integration of zinc sulfide with silver phosphate creates a Z-skin heterojunction that significantly improves the photocatalytic efficiency for degrading rhodamine B when exposed to visible light, demonstrating the effectiveness of this composite approach. Among the tested samples, the 10Z composite exhibited the lowest band gap energy of 1.82 eV, making it the most efficient photocatalyst for RHB degradation, highlighting the importance of catalyst composition in optimizing performance. The photodegradation of rhodamine B activity is significantly influenced by the effect of concentration, pH, catalytic dosage, and scavenging. And lastly, for the recombination, we can explore the use of silver phosphate zinc sulfide composite for degrading other pollutants such as organic compounds, heavy metals, and pharmaceutical waste. Conduct more comprehensive study using advanced analytical techniques like density functional theory and X-ray photoelectron spectroscopy to better understanding the catalyst properties and performance. And lastly, we can continue to optimizing reactions conditions such as the light intensity, the temperature to maximize the photocatalytic efficiency for various applications. Okay, that's all from me. Thank you.